Welcome to our webinar, Basics of Protection. These sessions are made for those who start working or who are new in the field of protection and where a solid understanding of relay protection for distribution and transmission grids is essential. My name is Gerd Einsiedler and I'm happy to guide you through this webinar. Some of you might already know me. I have been working in protection and automation for nearly 30 years. Since September 2023, I am part of Siemens Power Academy in Nuremberg as a certified trainer for protection. And today I'm introducing you to the basics of protection lectures. What is protection? How do we define a protection scheme? And since we receive a question rather often, yes, we will record the webinar and make the recording available and the slides available to all registered participants. If you already joined one of our last webinars, you already know the Q&A field in this application. Please type in your questions to the presenter in the question field. We will answer your question during the dedicated Q&A session after the series on 21st of June. In addition to me reading aloud your questions, you could also chat with our experts in the background. Please be aware of the following limitation. The chat is available in live mode only. Q&A questions will be answered via email if not managed during the live session. And just in case you are in full screen mode, press Escape to see the Q&A and chat box. And now let me introduce our expert, Professor Dr. Siegfried Lemmer. Siegfried Lemmer graduated and received his PhD at RWTH Aachen University. He joined Siemens in 1986. For many years he was head of the product lifecycle management for protection, where he was deeply involved in the design of C-Protect 4 and C-Protect 5 relay families. Within a master course of power engineering at Brandenburg University of Technology, Cottbus-Senftenberg, he presented lectures about protection for nearly 2 decades. In 2016, he retired from Siemens but continued his university lectures. Siegfried, and now we are curious to learn more about the basics of protection technology. The stage is yours.
Welcome to this introduction to protection. I would like to start here with a few very basic questions. What is protection? Why do we need protection? Where is protection installed in a network? Let's start with the first one. Why do we need protection? Against what does protection protect? If we look into our systems, components may have faults. You see here a nice photo of a thunderstorm hitting a substation, and it may start a short circuit in a substation. Another event could be street works, for instance, hitting a medium voltage cable in the street and also generating a short circuit there. That means short circuits will happen. Protection cannot protect against short circuits, but protection has to do something if a short circuit comes. The main focus in this introduction will be short circuits, but you should be aware that we also have other types of problems like interruptions, overloads, overvoltage, undervoltage, and so on. So there are a lot of other things which can happen. So why or what do we have to do after such a short circuit? If we have a short circuit on a line or on a cable, this device has to be separated from the rest of the system. It has to be switched off, and the decision to do that is the main job of protection. That means components which have faults must be disconnected. If we don't do that, what may happen? This nice picture shows such a situation. That is a picture from a real case. What you see here used to be a brand new transformer. During the commissioning phase, the different teams had some misunderstanding. That means in this case, the transformer was energized while the protection system was still not in operation. And unfortunately, this transformer had a problem in the bushing. That means when the transformer was energized, there was a short circuit in the bushing, big current flowing, and what you see here is the result of that thing because the protection didn't work. So you see, not proper working protection can have severe impact. It can produce damage, and even more, it can produce injuries of people if they are standing around there, or it can also endanger the stability of the whole system. That is mainly valid for transmission systems, for weaker transmission systems. Let me say for countries which are not interconnected very much to other countries. If in such smaller transmission systems, a short circuit remains there for too long time, and long can mean, for instance, 200, 300 milliseconds, then you can generate an instability of the whole system, which may lead to a collapse. So you see, protection is an important thing in the networks. And to understand where it is installed, we have to look a little bit into the network. This picture shows, just in a symbolic way, a grid, a transmission grid, which connects somehow the power stations with the cities and industry and so on. And these lines you see there are in reality, of course, bigger things that are not single lines. We always use three-phase systems. That means one line in this so-called single line diagram is equivalent to 3 lines on this tower. On the tower on the left-hand side, for instance, you see 2 systems, 2 times the 3 phases. What you also see is a so-called earth wire on top of the tower. This earth wire does not transport any energy normally. The reason for the earth wire is it is a lightning protection for the line, and it often also carries optical fibers for communication nowadays. What you also see in this picture is that every one of these 3 conductors of the system consists of 4 individual wires. That is state of the art for extra high voltage. It reduces the electrical field strength around the conductor. That's why it's a normal case for extra high voltage line. On the right-hand side, you see a distribution overhead line, medium voltage. In this case, 1 system, that means 3 conductors. And there we use just single conductors for the individual phases because the field strength is much lower there. If we now look at the connection points of this grid, that means the points where all these lines come together, it looks like this. There, every line, at the end of every line, we have a circuit breaker. Here you see 2 pictures of circuit breakers for high voltage systems. You again see the 3 phases. On the left-hand side, you see it for an open air switchyard. On the right-hand side, you see an indoor gas-insulated switchgear. And if we now zoom out this point a little bit more, it looks like this. That means we have not one point where all the lines come together. We have a so-called busbar, and all the outgoing feeders from this substation are connected to a busbar, and at the beginning of every feeder, you have such a circuit breaker and a protection relay installed. Always remember, this is a single line diagram. That means in reality, you have 3 bus bars available there. These slides here with the circuit breakers are pictures for transmission, for a transmission voltage level. The next slide shows the same story for a distribution level for medium voltage. In this case, it's an indoor substation. You see here the bus bar goes through this whole installation from left to right. And in every compartment, you see it's a big substation. We have many compartments there. In every compartment, you have one circuit breaker. The outgoing feeder goes down to the bottom. That means the cables are underneath. And you also see the protection relay installed there. If we now look a bit more in detail into such a feeder, it looks like this. You see on the left-hand side again the bus bar, and then I illustrated one feeder a bit more in detail. You see here the circuit breaker. That means that is the device which is really able to interrupt the short circuit current in case the line has a short circuit. Then we see current transformers and voltage transformers here. Why do we need that? The protection relay has to measure currents and voltages on the line to decide is there a short circuit or not. But as the line may have 20 kV, 132 kV, 400 kV or whatever, we cannot connect the line directly to the protection relay. We connect it via the so-called instrument transformers. That means the voltage is transformed down to a reasonable level, and also the big current which may flow, we may have 10, 20 kiloamps flowing in case of a short circuit. Also that is transformed down to a level which the protection relay can use. We typically also use a battery in a substation. It sounds a bit strange to have a battery in a substation which is full of power, but that battery is used to give a reliable supply both for the circuit breaker, for the whole control system, and also for the protection relay. And what is also indicated here is the wiring. Of course, wiring looks a little bit trivial in this sketch. Yes, it's trivial, but if you think about a big substation, open air substation, then you have the circuit breaker, the VTs and CTs outside in the field. You always have to multiply what you see here by 3, because we have the 3 phases. And the protection relays are somewhere in a relay house. And now you can imagine you have a lot of wires, and these wires can be 100 meters long or longer. So sometimes also things happen with the wiring, so that we sometimes also have to pay attention to that. We can compare this arrangement a little bit with what you know from your home. This is an MCB you have at home, and this one does protection for your low voltage system at home. And it's worth looking at the differences. What does this one do? What does our protection relay do in a substation? Their job is pretty much similar, but on the other hand, there are differences. This device here directly measures the current. In this case, it has only current. That means the current flows directly through this device. It makes the decision. If it says, okay, there is a short circuit, I will trip. It also interrupts the current. What our protection does is only half of that. It cannot measure the current directly. It gets the current and voltage measurement through current and voltage transformers. But the important thing, it cannot interrupt the current itself, it can only give a trip command to a circuit breaker. That means our protection relay roughly does half the job of such an MCB, but of course in a much more sophisticated way. What you also sometimes find is this arrangement, which is unfortunately a little bit more complicated. That is a so-called breaker and a half substation. It sounds a bit strange. Where do we have half a circuit breaker somewhere? What is the structure there? On both sides you see a bus bar, and to the top we have two outgoing feeders. And in this arrangement we again have one protection relay per feeder. The left protection relay for the left-hand feeder, the right protection relay for the right-hand feeders. But we have in total 1, 2, 3 circuit breakers. That means for 2 feeders we have 3 circuit breakers. That ends up in an average 1.5 circuit breaker per feeder. That means if we look at the left-hand relay, this is responsible for the left-hand feeder. If this relay detects a short circuit on the left feeder, it has to trip 2 circuit breakers, the left-hand circuit breaker and the center circuit breaker. The same applies to the right one. If that detects a short circuit on the right-hand feeder, it has to trip the center circuit breaker and the right circuit breaker. You also see voltage transformers and current transformers here. In this case, the situation with the voltage transformers is pretty easy. So we have a voltage transformer on the feeder. That means the left-hand relay measures the voltage on the left feeder. The same applies to the right one. The current measurement is a bit more tricky in this case. As you see here, the current transformer is not in the feeder. The current transformer is here, or several current transformers are here in this so-called diameter. Diameter is this horizontal connection between the 2 bus bars. And in order to measure the current in the feeder, for instance in the left-hand feeder, the protection relay has to sum up 2 current measurements in the diameter, and just by summing up the currents it can measure the current in the feeder. But the rest behind that, the protection principle, the way to identify short circuits, is the same as in the previous drawing. This is called breaker and a half substation, and the decision whether we build single line or double busbar substations or such a substation, that comes from the primary system, from the high voltage system. The protection people have to adapt to that. Let's also have a short look at the instrument transformers, just to show a few examples. On the left-hand side, you see a voltage transformer and a current transformer for medium voltage. You see here the connection points for the voltage and also for the current. That means the current flows through the current transformer this way. The primary current in the line is connected to this one. And our protection relay is then connected here in the bottom at these terminals, where we see the transformed voltage and also the transformed current. On the right-hand side, we see the same story for the higher voltage levels, in this case 400 kilovolt. In this case, you don't need more power in the current transformer and the voltage transformer. These things are just bigger because we need more insulation. Because we have to measure a voltage on a 400 kV level and need insulation for 400 kV. You see a current transformer for 400 kV. The current flow is here through the top of this thing. We also see a voltage transformer where the voltage is connected and our protection relay is connected somewhere down there. Just on the right-hand side, you see a combined instrument transformer. It is a combination of a current transformer and a voltage transformer in one device. Because normally we need both measurements, current and voltage. And what you also see here is again the three phases. That means if we talk about one voltage transformer, we normally talk about 3 devices, 1 per phase. Now let's talk a little bit about the requirements to protection, and there we often mention the 3 S. That means speed, safety and selectivity. So let's look at this a little bit more. What does speed mean? Imagine speed is pretty important. Remember, short circuit, lot of current flowing, risk of damage and of components. That means we must be fast to disconnect the fault if we detect one. And in protection, fast means something like a few milliseconds up to 100 milliseconds, or in cases even more when we have to do compromises. Getting enough speed is, on one hand, a question of the algorithms. That means on the manufacturer side, developers have to invest brain into fast algorithms, especially for the high voltage, extra high voltage levels. But speed is also influenced by the protection concepts. And you will see in the second part of this webinar that we sometimes have to do compromises when building up the protection concepts, which will lead to delayed tripping. That means we have to reduce speed for some reasons. The second point is safety. Think it's self-understanding. It's technology. If our technology doesn't work properly, there is a risk of damage or injuring people or instability. That means we have to think about the reliability of the whole system. And there will be a separate chapter on that. And the last issue, which also has to be mentioned, is the selectivity. What does selectivity mean? Selectivity means if you have a short circuit somewhere in the network, there is short circuit coming through different lines, cables and transformers. That means several devices in the system will see there is something wrong. But only the protection device of the faulty line or cable has to trip. The other ones see the fault, but they should not trip, because we don't want to trip 5 lines if there's a short circuit on one line. And this thing is called selectivity, that only the faulty component is disconnected from the rest. And that is a very important issue, and we will have several chapters dealing what can we do to get selectivity. That is the end of this basic chapter of this introduction. And in the next chapter, we will see what aspects do we have to consider if we want to put together a protection scheme. Thank you. So what aspects do we have to consider if we want to define a protection scheme? So you already realize there is a strong relation between protection and the network. That means we have to look a little bit into the network. And the first question is, of course, what type of component do we want to protect? This picture just shows a mixture of all the different components which may be available in the network. Of course, the majorities are lines and cables, transformers. What you also see here is generators, motors, and other special things. Busbars is also important. The focus here in this introduction will mainly be on network components. That means transformers, busbars, cable, and lines. The focus will not be generator protection and motor protection, because there a lot of different things have to be considered. So one thing is the type of component. The next thing we have to look at is the voltage level. This starts from the extra high voltage level, from the transmission network level, and it depends on the country, on the area of the world where we are, which voltage level we find there. It can be something between 220, 400 kilovolt, 750 kilovolt, or trials are already done with even higher voltages. The voltage level which is used depends on the size of the country, the distances, and the amount of energy we have to transport. Always remember, for the protection relay, the voltage level doesn't make a big difference because the voltage is always transformed down to that level which is seen by the relay. But the concepts to do protection are different in high voltage level compared with medium voltage. Below high voltage, you have typically so-called subtransmission level. Also there, the voltages are different in different areas, 110, 132 or 150 kilovolt. And below that, you have a medium voltage level, which does really the distribution of the energy into the cities, the villages. These are often cable systems, but it can also be overhead lines like shown in these pictures. And the voltage levels we cover here with the technology, with this technology, starts typically from 6 kilovolt up to, for instance, 30 kilovolts in the medium voltage level. That are the voltage levels. We also have to look into the network structures, and they depend a bit on the voltage level. What you see here is a mesh network. That is what you typically find in transmission systems, in subtransmission systems. That means we have a mesh system which has grown somehow, which connects the power station, the generation, and the loads. That means the transformers you see here connect the power station to the grid, and they can also be connections from these transmission networks to subtransmission or to distribution. Important thing here that is important for protection is we have a meshed structure. That means if we have a short circuit somewhere on one line, the current comes from different sides from different directions into our line. And that is an important fact to define the protection. Another type of network is shown here. That is a typical network we often find in distribution systems. We have one busbar, which gets its energy from in-feeding transformers. And then from the busbar, we have so-called radial feeders. That means feeders with different substations, transformer stations in between. And these transformers transform then down from the distribution level, 20 kV, down to the low voltage level, 0.4 kV. And the important thing is that these feeders are radial. That means on the bottom here, these connections are open. That means we have a system with no meshes. The system is radial. And the important thing is, if you have a short circuit on one cable, for instance on this cable, the short circuit current comes through the transformer, the busbar, to this cable. It comes from one side, and that is a very important feature when we design the protection system. You may ask the question now, why do we have these strange connections here on the bottom? The reason is the following. Imagine you have one cable destroyed, for instance by street work, In the moment the cable is destroyed, you typically have a short circuit. Then the protection will disconnect this cable to remove the short circuit. But then the bottom transformer here is without energy. And what you can do then is you can remove the destroyed cable from the network and then close this connection point here on the bottom and resupply this transformer here through the connection from the other side. That means normally you have a radial system, and we will see that's important for protection. After protection has worked, you can reconfigure the system. That will take some time, depending whether you have remote control or you have to drive there to reconnect that. Important point here is normal operation is a radial system. Similar things are normally visible in industrial systems, like shown here. These systems are often also radial. The difference in comparison to the public distribution systems is that here the distances are normally shorter. So we are here within one plant, chemical plant or refinery. Distances are shorter, and we normally have a lot of motors involved here. But also there, the main question for protection is, do we have meshes or is the system a radial system? That was the system structure. The next point we have to consider is the neutral earthing. And that is a point which has really big impact on protection. What we see here is the one side of a transformer in the system, and this transformer has a star point. And now the big question is, what do we do with the several star points in the system? One thing you can do is so-called solid earthing. That means you connect the star points to ground. And that is what you typically do in transmission systems. There normally the star points are grounded. What does that mean? That means if you have a short circuit, a single phase short circuit, or if you have a connection to ground, which is the most probable type of short circuit, then you have really a short circuit loop here. And that means if you have this type of fault, connection of one phase to ground, you have really a short circuit with a big short circuit current. If you want to reduce the short circuit current, you can add a resistor here in the star point. If you again imagine this connection to ground and look at this short circuit loop, you now have the resistor in this loop. And that means by this resistor, you can limit the short circuit current. And for some cases, especially in distribution systems, this is done. Because for the most probable type of fault, you have then a reduced short circuit current, which means the risk of damage, of injury of people and so on is lower. But that refers only to phase to ground fault. That does not influence the short circuit current in case of a phase-to-phase fault. And you can do even more things. You can put in a reactance here. And with such a reactance, you can bring down the short circuit current even to zero, or you can leave this open. That means in such a case, if you have such an arrangement, if you have a reactance here or if you have the star point open, you have pretty low currents in case of a phase to ground fault. You can even continue operation without risk of damage. So the earth fault in this case is not really a short circuit because there's only small current flowing. That's the good thing. But on the other hand, you must find that fault. You cannot. You can continue operation for seconds, even for minutes, but you must find this type of fault. That means in such a case, you must have additional protection functions to identify and to look to find out where this type of fault is. So that is a special area of protection in these networks. That means if you think about a protection system for a network, you must have a look at this star point treatment. As I said, transmission system, you are typically with solid earthing. In distribution and industrial systems, you find a lot of other different things. That was the neutral earthing. And the last thing I'd like to mention is here, what types of fault do we have to consider? On the left-hand side, on the bottom, you see the most frequent type of fault, single phase to ground fault. This will occur typically, for instance, if a lightning arc hits an overhead line, you have an overvoltage there, you get a flashover on a tower, and then you have a phase to ground fault. And you can assume that roughly in an overhead line system, roughly 80 to 90% of all short circuits are single phase to ground short circuits. Sometimes they evolve to a phase to ground fault. That means if you have on one tower a lightning arc burning, a short circuit burning on the tower, there's a lot of hot air flowing around there, and that sometimes affects also another phase. Then you get this phase to ground error fault. And of course, you can also have just a short circuit between two phases. For instance, if the conductors of an overhead line start some oscillations. And of course, there is also a risk of a three-phase short circuit. That is not very often. The typical thing, for instance, would be in a distribution system. You have roadworks there, people opening the street, didn't look at the cable plans before, excavator hits the cable, and either you get an interruption or you get a short circuit, or both. That's one reason why you have three-phase short circuits. Another reason can be you did maintenance on a line. If you do maintenance on a line, you have to ground the line. That means you have to connect all the three phases together to ground. Then you can work on the line. After you have finished your work, you want to reconnect the line. And if you then forget that the grounding is still there and energize the line, you have a three-phase short circuit and the protection has to trip. So that are the types of short circuit. On the right-hand side, you also see other types of faults like interruptions. They are not so critical normally. A three-phase interruption means we have no longer transport of energy. The other side is maybe without voltage, but it's not such a critical thing that something explodes. But if you, for instance, supply a big motor in a chemical plant, for instance, and you have a single-phase interruption, a motor doesn't like that, or a generator, because these motors and generators need a three-phase system to have a constant torque. And if one phase is missing, you can destroy the devices. So for that reason, also these types of faults have sometimes to be disconnected. So we come to the end of this chapter. We looked at the different aspects of the network which have to be considered to bring together a protection scheme. And in the next chapter, we will look at the protection principles which are available to detect short circuits.
Thank you, Siegfried. That has been an interesting session with insights into the basics of protection technology. Dear auditorium, thanks a lot for your questions. We will answer these in the Q&A session on June 21. If questions come into your mind later, or you would like to go for more details, please visit our training platform at Siemens Power Academy. I'm sure you will find the right information and the right training. The access to the recording and the slides will be sent to all participants. Thank you very much for your active participation. It was a pleasure for me to guide you through this first session on basics of protection technology. In this session, we learned what a protection is and why we need it, and how to define a protection scheme. I'm looking forward to meeting you soon in the second session of Basics of Protection on 4th of June, which is focusing on which protection principles do we use, what is the earth current, what are primary and secondary values. Stay safe and sound, take care and goodbye.